So hello guys and welcome to the lecture of transmission line designs. Today in this video we will see important numericals based on transmission line designs. So here you can see a numericals and this numerical is normally asked in 15 marks and this is one of the important numericals asked in Pokhara University. So here you can see design a transmission line to transmit 3-phase 85 megawatt at 0.9 power factor lagging over a distance of 160 kilometers, and the voltage regulation should be within 12.5% of receiving in voltage, means the voltage regulation should not exceed 12.5%, and the efficiency is given as here 95%, and corona loss not to be exceed 0.6 kilowatt per kilometers, and here the corona loss should not exceed 0.6 kilowatt per kilometers, and here we have to calculate. First we have to choose the voltage and then the size of conductors and the spacing between conductors, and in the second one we have to calculate the line constants and we have to determine the voltage regulation too. Similarly, in third point we have to find the efficiency at full load, and the last but not the least, here we have to predict the corona loss per kilometer of the lines and the total corona loss. So let's start. So before starting we have to choose the economical voltage. So for that, here we have the formula for most economical voltage. Here we have most economical voltage given as V equals to here 5.5, and in root under we have L in kilometer upon 1.6 plus power in kilowatt upon 150 NC into cos 5, and here NC is the number of circuit required, and here the most economical voltage, the value will be in kilovolt here. So this is the empirical formula to calculate the most economical voltage, and if you substitute here, we know we have given the length in kilometer as here 160 kilometer. Similarly, P in kilowatt is given as here in the question as 85 megawatt, and the unknown factor is here we have NC. So and power factor is also given, so 1 means 0.9, and if you substitute the value of NC here, you can see for single circuit, if you substitute NC as 1, we will get the value as V equals to 148.56 kilovolt. Similarly, for double circuit line means NC equals to 2, we can calculate V as V equals to 112.018 kilovolt, and here we will choose 132 kilovolt as the standard voltage. Normally the standard voltage we choose as 132 kilovolt, and the next higher one is 220 kilovolt, and here first we'll choose 132 kilovolt as the standard voltage, and then we'll check for power triangle capability. So checking for power triangle capability applying, so first we'll calculate the P1s, means power transfer capability of for single circuit lines. For single circuit means 132 kilovolt line, we have P1 is equals to MF into SIL, and here the value of EMF can be obtained from the table. So MF is 2.25. So you will be given the table, and from table you will use MF as 2.25. So 2.25 into source impedance loading of first single circuit. So for SIL you can write here kV upon means impedance, and along with the table you will also given the value of ZC here. So in the table above you will be given the value of ZC as 400 ohm, means here I have not got the table right now. So 400 ohm. So if you calculate the value of P1, you will get here 98.01 megawatt. Similarly, power transfer capability for double circuit line will be P2 is equals to MF into SIL, and MF is given as 2.25 and SIL means kV upon ZC, and now in double circuit line the impedance will be halved, means 400, you have given ZC as 400, for double circuit will be 200. So if you calculate, you will get here 196.02 megawatt, and here we have a power given as 85 megawatt. So in conclusion you can write here, since power capability of single circuit is enough to transfer 85 megawatt, so choosing single circuit lines. So this power capability for single circuit is enough to transfer 85 megawatt. So here we'll choose the single circuit lines. So here Selection of conductors. So for that, first we will have to calculate the receiving end current. So we have IR is equals to P upon root 3 VR into cos phi, and P is given as 85 megawatt. So we'll use the value of P in kilowatt, and the value of VR is already given in kilovolt. So 85,000 upon root 3 and VR in kilovolt upon cos phi means 0.9. So we'll get here 413 amperes. Now we can see, now here from we have to calculate, we have to choose the conductors. So here after calculating value of IR means receiving current, we have obtained as 413 amperes. So you can see in table here right now. So this is the means here approximate current carrying capacity at 40 degree ampere temperature. Here we have 430 ampere given as here. For wool conductor here we have 430 and we have calculated as 430. So it is nearer to 430. So here we will choose wool conductors means here we have obtained the value of IR as 413. So from table we will choose the wool conductor means 430. It is approximate to 430. So we'll choose here wool conductor here. So after choosing wool conductors, we can here resistance at 20 degree means R20 is given as 0.188 ohm per kilometer. So you can see into a table here for wool conductors the value at R20 means here we have the column for calculate resistance at 20 degree when connected to a standard watt ohm per kilometer. So at R20 the value of R20 is 0.18440, or directly we can calculate the value of R75 at 75 degrees Celsius. Here we have given as 0.2258. So either you can use R20 or you can use R75. So if you use R20 we have to calculate the value of R75, and so to avoid time or to manage times here we can directly use the value of R75. So R75 is given as 0.22538. So here first I have here from table I have obtained the value of R20 as 0.188, and then I have calculated the value for R2 means at R75. So here we have to check the efficiency limitation means efficiency should be greater or equals to 95%. And similarly for diameter in the table you can see the diameter for given as 18.13 mm. You can check the table. So we have to calculate the value of R75. So R75 we have to calculate as R20 into 1 plus 75 alpha plus 1 plus 20 alpha means here, and the value of alpha means the temperature coefficient of resistance, and it is given as 0.004. So the value of R75 will be 0.226 ohm per kilometer. Now we have to calculate the PL. So we have PL is equal to 3 square into R75, and here 3 into, you have just calculated the value of IR as 413 here, 413 ampere. So 413 into R75, and here we have R75 as 0.226 ohm per kilometer. So 0. ohm per kilometers, and per kilometer means, and the length is given as 160 kilometers. So we will get here 18.50 megawatt. Similarly, if you calculate the efficiency, we'll get efficiency as P naught upon P naught plus PL. And in the question, you have given as 85 megawatt. Similarly, P naught is 85 plus PL, and just now we have calculated the value of PL, and PL is 18.50 megawatt. So if you calculate here 80, will get here efficiency as 82.12%. Since the efficiency is less than 95%, so we'll choose the next higher standard voltage means 220 kilovolt. So if you choose 220 kilovolt, the value of IR will be P upon root 3 VR cos phi, and you will get here 248 amperes. Similarly, PL will be 3 IR square into R75. So if you calculate, we will get here 6.61 megawatt. Similarly, efficiency will be 90. If you on calculating get the efficiency as 93%, and here still the efficiency is less than 95%. So choosing the next higher size conductors. So here let's choose ship conductors, and from the ship conductor table you can use the value of R20 as R20 equal to 0.079 ohm per kilometers and the diameter is 27.93 mm. So you can check the table to know the value of R20 and the respective diameters for ship conductors. Similarly, if you calculate the value at R75, we will get here 0.09 ohm per kilometers. So to calculate PL, we have PL as 3 IR square into R75, and now IR we will use IR, the value of IR as 248, and R75 is 0.095 per kilometer. So for each kilometer we have 160 kilometer here. So if you multiply with 160 kilometer, you will get here 2.80 megawatt. Similarly, efficiency will be P naught upon P naught plus PL into 100%. So when calculating, we will get here 96.81%. So efficiency is greater than 95% in this case, so it is acceptable. So we'll choose the ship conductors. Now spacing between conductors. So for line voltage for 132 kilovolt, the spacing between conductor is taken as 3.5 meters. Similarly for 220 kilovolt, the spacing is taken as 6 meters. Similarly for 400 kilovolt, the spacing is taken as 11.5 kilometers. And for 765 kilovolt, the spacing is taken as 14 meters. So here we have choose the economical voltage as 220 kilovolt. So for 220 kilovolt, we have the respective spacing is given as 6 meter here even in the questions. And so for 6 meters and considering the horizontal configurations, so if you consider these horizontal configurations, so the D equivalent will be, so if you consider this as a reference, so from here if you calculate, so from here to here we have 6 meters, again from here to here we have 6 plus 6 12, so 6 into 12. Similarly from here if we take this as the reference, so from here to here we will get 6 meters. Similarly from here to here 6 meters, and similarly at last if you take it as a reference, so from here to here we have 6. Similarly from here to here we have 6 plus 6 12, so 6 into 12 into 6 into 6 into 6 into 12 and to the power 1 upon 6, so we'll get here 7.56 meters. Now in the second you have to calculate the line constants and the voltage regulations, and here the line length is greater than 100 kilometers, so you can consider it as a medium line length. And here we'll use the pi representations. So for pi representations, the line constant is represented here for A, B, C and D. So for A we have 1 plus yz upon 2. Similarly for B we have z, and for C we have y into 1 plus yz upon 4, and for D we have 1 plus yz upon 2. And we know z is equals to r plus jxls, and the value of r we have just now obtained the value of r. Here the r is 0.09 ohm per kilometers. So 0.09 into per kilometers, so we have 160 kilometer given, 160 kilometer line, so 0.095 into 100 will get here 15 ohms. And we know y equal to 1 upon xc means j omega c, and in order to calculate the xl, we know xl equals to 2 pi fl, and where l will be l equals to 2 into 10 to the power minus 6 log t equivalent by r. So 2 into 10 to the power 6 log, and the value of d equivalent is 7.56, and the value of r dash is here 0.7788 into r. So a is 13.965 mm, means 13.965 into 10 to the power 3 means the 10 to the power 3 is 10 to the power minus 3 is taken in the here numerator terms. So to calculate xl, just now we have calculated the value of here L here, and if you substitute the value of L into here, so you'll get xl as 2 pi fl into means 160 kilometers, and 160 into thousands, so you'll get n meters, means the value of xl will be 66 ohm per phase. And to calculate the capacitance, we know C is equals to 2 pi epsilon upon log D equivalent of R. So 2 pi into value of epsilon is 8.85 into 10 to the power minus 12 upon log D equivalent means 7.56 upon R. The value of R is 13.96 mm. So 13.96 into 10 to the power minus 3, and it is taken above in the here numerator terms, Faraday per meters. And now if you calculate the value of C, we'll use here C is equals to 2 pi into 8.85 into the minus 12 upon log D equivalent of R into 1000 into means Faraday per meter. Here we have given, so we have to calculate in Faraday, and altogether we have given 160 kilometer lines. So So 162 into 1000, so we'll get in Faraday. So we'll get here C as 1.43 into 10 power minus 6 Faraday. And Y is calculated Y equal to j omega C. And here the value of C is here 1.43 into 10 minus 6. So if you substitute the value of Y means C, we'll get the value of Y. So Y will be J 4.43 into 10 minus 3 mho, which is in imaginary terms. Similarly, Z will be R plus JX, will get 15.J6. So if you substitute the value of Z and Y, will get the respective parameters, means line constants A as A, and here we have A equals to D as 1 plus YZ upon 2. So if you substitute the value of Y and Z, you will get here their respective value. Similarly, we will calculate the value of B. Similarly, we will get the value C. And now we know here we have Vs and Is and the respective parameter A, B, C and D, and here we have Vr and Ir. So Vs will be A Vr plus B into Ir, and Vs equals to we have just calculated the value of A, B, and means all the line constant means A, B, C and D. If you substitute the value of A and B, similarly, and Vr and Ir, we have Vr and Ir is known. So Vs equals to, and Vs equals to A into Vr, and a value of A is 0.985 into J 3.323 into 10 minus 3 into, and the Vr is 220 kilovolts, so 220 into 1000 upon root 3, plus the value of B is 15.J66 into, and IR is 248, and the angle will be here the 0.9 power factor, so minus 25.8 for this. So in magnitude form we will get here Vs as 136619, and its angle is 5.5 volt, 5.5 degree. And similarly we will get Is as Is equal to C into Vr plus D into Ir. So C into Vr equal to 220 kilovolt means 220 into 1000 upon root 3. So D into 248, and its angle is minus 25.84 degree. So if you calculate it in the form of R and theta, so you'll get here 225.46, and angle will be minus 12.75 amperes. So percentage of voltage regulation will be Vs minus Vr upon Vr into 100%. So if you calculate, you will get here 7.55%. And since 7.55% is less than 12.5%, so it is acceptable. And here from voltage phasor diagrams, here you know Vs, we have calculated the value of Vs as 13661, and its angle is 5.5. Similarly for Is, its angle is here minus 12.75. So if you draw the voltage phasor diagrams, and the value of cos phi should be cos this 5.5 plus 12.75, so will be total the value of cos phi should be 0.9496. So efficiency will be P naught upon P naught plus losses, so P naught upon P in. So and value of P naught is calculated Vr Ir into cos phi r. Similarly for P in, we can calculate as Vs Is into cos phi s, and Vr will be 220 upon root 3, and Ir is given as 248, and power factor is 0.9, and Vs will be here. Just now we have calculated here the value of Vs means 136619, and into Is, and we have also calculated the value of Is as here 225.46, and the cos phi s means cos phi is 0.9496 means 0.9496, so you'll get efficiency as 96%. Now to calculate the corona loss, we have the critical destructive voltage. The formula for critical destructive voltage is Vd equals to 3 into 1 upon root 2 into R into del into M into log D equivalent upon R into 10 power 6 volt per phase. And here del is the density of air means, and it can be calculated as 3.86 P upon 273 plus theta, and 3.86 into, and value of P will be 76 cm of Hg, and 273 plus theta, and means room temperature is 25 degrees Celsius, so you'll get as 0.98. Similarly, and here we have the term as M, and M represents the roughness factors here, and roughness factor 0.82, and its value is 0.84 SCSR conductors. Now if we substitute all the parameters, you will get the value of Vd as Vd equals 3 into 1 upon root 2, and the value of R is 13.96 mm, so 13.96 upon 1000 into del, value of the del is 0.92, and roughness factor is 0.82 into log D equivalent R into 10 power 6, so you'll get here 149.25 kilovolt per phase, and the ratio V upon Vd is calculated as on calculating, we'll get here 0.85. and if there is a V upon Vd is greater than 1.8, we use peak formula for corona loss, and the peak formula for corona loss is P equals to 243.5 A plus 25 upon dl and root and R upon d equivalent V minus Vd square into 10 by minus 5 kilowatt per kilometer. Similarly, if there is a V upon Vd is less than 1.8, we use Peterson formula here. Peterson formula for corona loss, and here the Peterson formula for corona loss is 21 Newton by 6 F V square upon log base 10 D upon R square into F kilowatt per kilometer, and where the factor F, and here you can see there is a V upon Vd is 0.85. So 0.85 is here less than 1.8. So here we will use Peterson formula for corona loss. So if you use Peterson formula, you get 21 into 10 minus 6 F V square upon log base 10 D upon R into F, and there from table we can use the value of F as here. The safety factor is here, the ratio is V upon Vd is 0.85. So for 0.85 we have the factor F as 0.018. So here we have used 0.018. So when calculating we will get PL as 0.0407 kilowatt per kilometer, and the total corona loss will be 0.0407 kilowatt per kilometer into 60, means 160 kilometer line is given. So you get here 6.517 kilowatt. So in this you can solve such type of numericals related to transmission line designs. Thanks for watching this, and please don't forget to subscribe to my channel.